Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Methods for Scientists and Engineers by K. Shankar Rao. We will continue to discuss topics from Module 2, Numerical Methods in Physics. In the last class, I introduced the concept of finite difference. In today's class, let's see how to do numerical interpolation using the forward difference method. This is also known as Newton's forward difference interpolation. So once again, we have n data points which we obtained by performing an experiment. So these are the experimental data points x0, y0, x1, y1 all the way to xn minus 1, yn minus 1. So these are the n experimental data points. Remember, x1, x2, x3 are equally spaced. We do not know the explicit relation between x and y, so our aim is to find a function f of x which connects x and y values. So once I know f of x, for any given x I can calculate the corresponding y value. That's the idea. So in general, f of x is an nth degree polynomial yn of x. So our relation is going to be y equal to yn of x. Now the general form of this nth degree polynomial is going to be yn of x equal to a0 plus a1 x minus x0 plus a2 x minus x0 into x minus x1 plus a3 x minus x0 into x minus x1 into x minus x2 plus all the way to infinity, or all the way to the end. Okay. As I said, all the x values are equally spaced. So let's say the difference between two successive x values is the step size h. So I can write x1 equal to x0 plus h. Similarly, x2 is equal to x1 plus h, or x0 plus 2h. Similarly, x3 is going to be x0 plus 3h. Or if you take the difference of two successive x values, x1 minus x0, this is going to be h, or x2 minus x1, this is going to be h, or x2 minus x0, this is going to be 2h. Okay. Now, if I want to get the exact equation, I need to find out the values of these unknown constants a1, a0, a1, a2, a3, etc. So let's try to do that. First, let's go to the first data point, which is x0, y0. Okay. So at this data point, corresponding to x0, I have two y values. One is the experimental value y0. Second is the theoretical value, which is yn of x0. Okay. So if the experiment and theory exactly matches at this point, then the theoretical value yn of x0 should be equal to the experimental value y0. Okay. So let's find out what is yn of x0. So in this equation, in the place of x, you just write x0. That will give you yn of x0. So that's going to be a0 plus a1 into x0 minus x0. So the second term vanishes. In the third term also, I will have x0 minus x0. That also vanishes. So basically, all the subsequent terms are going to vanish. So I'm left with only a0. So a0 equal to y0. So I find the value of the first constant. This is y0. Now to find out the value of second constant a1, I go to the second data point x1, y1. Once again, if the theoretical value exactly matches with the experimental value, then y1 will be equal to yn of x1. So there is a perfect agreement between theory and experiment. Now I can find out what is yn of x1. So substitute for x in this equation. So y1 is equal to a0. a0 is nothing but y0. So this is y0 plus a1 into x1 minus x0 plus a2 into x1 minus x0 into x1 minus x1. So this is going to be 0, so the second term vanishes. If you look at the third term, here also I have x1 minus x1, so the third term also vanishes. Basically all the subsequent terms are going to get vanished. So I am left with y1 equal to y0 plus a1 into x1 minus x0. x1 minus x0 is the step size h, so I can write y1 equal to y0 plus a1 into h. By rearranging the terms, I can write a1 equal to y1 minus y0 divided by h, and y1 minus y0 is nothing but the first forward difference term delta y0. So a1 equal to delta y0 divided by h. I hope now you have understood the general methodology, right? So if you want to find out the constant a2, basically you have to go to the third set of data points x2, y2, follow the same procedure, and you will find that a2 equal to delta square y0 divided by 2 factorial by h square. So this is the general form of the equation. So the next term you can write straight away without doing any derivation. A3 is going to be delta cube y0 divided by 3 factorial into h cube. Same way you can find all other constants. So once you find the values of a0, a1, a2, etc., you can substitute it back into equation 1. So that will give you the final form of the nth degree polynomial yn of x equal to y0 plus x minus x0 by h into delta y0 plus x minus x0 into x minus x1 divided by 2 factorial h square multiplied by delta square y0 plus all the way to the nth term, or the n minus 1th difference term. Okay. Now if you look at this equation, x minus x0 by h, this is a common factor from the second term onwards, so I am going to define it as p, x minus x0 by h equal to p. I can rewrite this equation in terms of p. That will give a nice shape to this equation. So my nth degree polynomial connecting the x and y values, yn of x equal to y0 plus p into delta y0 plus p into p minus 1 delta square y0 over 2 factorial plus p into p minus 1 into p minus 2 into delta cube y0 over 3 factorial all the way to the n minus 1th difference. Okay. So this is known as Newton's forward difference interpolation formula, and if you look at this formula closely, you can see that y0 is the leading term in the difference table which we have derived in the previous class. Delta y0, delta square y0, delta q y0, etc. are the leading difference. That's why when we formed the difference table in the last class, I said the first diagonal row is very important because you are going to write the function in terms of the leading terms and the leading differences. So that's why formation of the difference table is the most important step in numerical interpolation. Now let's do one simple problem so that the process will be familiar to you. Given the following table of readings, find the value of y corresponding to x equal to 0.16. Okay, so you are given x and y values, x equal to 0.1, 0.2, 0.3, 0.4, and these are the corresponding y values. So first thing, check whether x values are equispaced. So you can find the difference between any two successive x values is a constant 0.1. So your step size is a constant. Okay. Now you are asked to find the y value corresponding to x equal to 0.16. So this is not a value among the experimental observation. So if you want to find the value of y, you need to find it theoretically. So basically you have to find the function yn of x which connects x and y values. Once you find yn of x, Substitute for x equal to 0.16, you will get the corresponding y value. Okay. Now how to find y of x? First you have to form the difference table. Okay. You will know how to form the difference table. We have done this exercise in the previous class. Okay. First write down the x and y values in two columns. So totally how many number of data points are there? 1, 2, 3, 4. So if I have 4 data points, I have to find difference terms up to 4 minus 1, which is 3. So basically I need to find delta y, delta square y and delta cube y. Okay. Let's first find out the first difference terms. So take the difference between the successive y values 1.020 minus 1.005, 0.015. Similarly, you find all other terms. Then find the difference between the successive first difference terms. That will give you the second difference term. So 0.025 minus 0.015. This is 0.010. Similarly, find the difference between the successive second difference term. That will give you the third difference term. Okay, so the difference table is set and the first diagonal row. These are the leading terms and leading differences. Okay, so to find out the polynomial yn of x, you are going to use these steps. Okay. So what all information we have? We know x equal to 0.16 and step size h equal to 0.1. We need to calculate p. P is x minus x naught by h. This is equal to 0.16 minus x naught 0.1 divided by h 0.1. This is 0.6. And we know delta, we know y naught, delta y naught, delta square y naught, delta cube y naught. Basically all the information is available. Now straight away substitute in the equation. Since we have 4 data points, we need to write terms up to delta cube y naught. Okay. Now substitute the values. Y naught equal to 1.005 plus p is 0.6. Sorry for the typo here. This should have been 0.6 multiplied by delta y naught, which is 0.015. Similarly, you substitute for all other terms, you get this is equal to 1.012856. So y value corresponding to x equal to 1.6 is this much. Okay, so this is how you do numerical interpolation using Newton's forward difference. To get more practice, you can do a homework. Estimate the population in lakhs in a city in the year 1955 based on the following data with the accuracy of a 5th degree polynomial. So these are your x and y values. X is the year, y is population in lakhs. You are asked to find out the y value corresponding to x equal to 1955. So here 1, 2, 3, 4, 5, 6, 7 data points are there, which means you have to find difference terms up to the 6th order. But it is mentioned that your polynomial need not go all the way to the 6th order. You can stop at the 5th degree. So basically you have 2 more extra terms in this equation. P into P minus 1 into P minus 2 into P minus 3 divided by 4 factorial delta to the power 4 y naught plus P into P minus 1 into P minus 2 into P minus 3 into P minus 4 divided by 5 factorial into delta to the power 5 y naught. Okay, so follow the same procedure, you can find the answer. So that's an assignment for you. So the next question is how to do this interpolation using Python programming platform. Okay. So in the last class we have discussed about the Python program for finding the difference table. So in this program also, if you see, half the problem is about finding the difference table. So we already know that. So this program is going to be very easy for you. So as a representative program, I am going to write a program with 5 data pairs. Okay. So almost the half of the program, or 70% of the program, is exactly same as the previous day's program. So basically you need to create 2 lists of x and y values. So x data, y data, I am initializing it as an empty list. Then I need to have the number of data pairs, which I am going to input as an integer, n equal to int input, enter the number of data sets. Then I am going to input the x and y values using a for loop. So I am going to use the split function so that I can input x and y simultaneously. As and when I input x and y, I am going to append it to the existing list. So I have x and y columns ready. Now I need to input the x value at which I want to do interpolation. So x equal to float, input, enter the data point for interpolation. Then I need to calculate the step size, which is the difference between any 2 successive x values. So I am going to find x1 minus x0. So this is h equal to x data 1 minus x data 0. Once I find h, I can find p equal to x minus x data 0 divided by h. Okay. Now I need to find the difference terms. Since I have 5 data pairs, I need to find the difference terms up to 4th order. So I'm going to call those lists as D1, D2, D3, D4. Just like the previous case, I am going to initialize all the elements to 0. So this is equal to 0 into n. So I have a list of n elements. All the elements are 0. I am going to modify the elements in the next section. First, let's find out the elements of the first difference list, D1. So the first difference is nothing but the difference between successive y values. Okay. So here I will have one element less. Okay. So for I in range 0 to n minus 1, D1 of I equal to y data I plus 1 minus y data I. Once you find the D1 values, you can find the D2 values. This is going to be the difference between the successive D1 values. Here one element will be less compared to D1. So for I in range 0 to n minus 2, D2 I equal to D1 I plus 1 minus D1 I. Same way you find out D3 and D4. Okay. So once I have all the parameters ready, I can directly substitute in the equation. But if you look at the equation, this is very cumbersome. So if you write it in the Python, using the Python syntax, you are going to have a very bulky equation. So what we are going to do is, let's simplify all these coefficients. Okay. So the coefficient of the 0th term is 1. So let's leave it that way. The coefficient for the first term, I am going to call it as C1. Okay. So C1 equal to P. And the coefficient for the second term, P into P minus 1 divided by 2 factorial is 2. So P into P minus 1 by 2. P is C1, right? So this is going to be C1 into P minus 1 by 2. So C2 equal to C1 into P minus 1 by 2. Now the next coefficient, I am going to call it as C3. So C3 equal to P into P minus 1 into P minus 2 divided by 3 factorial. 3 factorial is 2 into 3. But P into P minus 1 by 2 is nothing but C2, right? So I can write it as C2 into P minus 2 divided by 3. So C3 equal to C2 into P minus 2 by 3. Same way you can write C4 equal to C3 into P minus 3 by 4. So once you have defined all the coefficients, now you can write y equal to the leading term y data 0 plus C1 into the first leading difference D1 of 0 plus C2 into second leading difference D2 of 0 plus C3 into third leading difference D3 of 0 plus C4 into fourth leading difference d4 of 0. Okay, so this is your yn of x, nth degree polynomial. So finally you can write print the interpolated value for %f is %f %x comma y. Finally you can say enter or thank. Okay. So once again, this is not a great program. I had taken it from the reference book just for the sake of accessibility. Just like the previous program, here also the scope is limited because this program works explicitly for 5 data pairs. So if you want to do interpolation with 6 data pairs, you have to make changes to this program. Anyway, this is good for a beginning. If you are interested, you can write a code for a general scenario. Okay, so those who are interested can do that as an assignment. Okay. So that's for today. In the next class, we will discuss about numerical differentiation, which is also based on the difference table. Thank you.